Please welcome Juergen Schmidhuber.
Three prisoners were sentenced to death, one of them French, one of them German, one of them American. What is your last wish? They ask the French guy. He says, one exquisite bottle of exquisite French wine. What is your last wish? They ask the German guy. He says, I want to give a speech. What is your last wish? They ask the American guy. He says, I want to get shot before the German starts his speech. Unfortunately for you guys, it is too late now. Up there is the title of my talk, and this is my name. This is how to pronounce my name. And all the things I'm going to talk about are in many papers on web pages, and you can get overviews more than you wish if you go to these pages or Google for keywords. I'm affiliated with the ITSIA, the Swiss AI Lab in Lugano, and I also have a group at the Technische Universität München, Tech University Munich, where there are a couple of pioneering robots. All my slides are designed according to recursive applications of the harmonic proportion, the golden ratio, and that makes them very compressible, and therefore has a lot to do with my talk, because it's all about compression and compression progress. But before I come to that, let me just make a few general comments. Lots of people, especially at this conference, are talking about the future, but it's much harder to shape the future. And I'm going to show you a shaper. Here we see him. He was mentioned before. Markus Hutter, a couple of years ago, did a postdoc in my lab in Switzerland, but now he's a professor in Canberra, and he came up with this algorithm that every computer scientist should know, a universal problem-solving algorithm which takes any well-defined problem as an input and computes the solution to this problem as quickly as the fastest unknown algorithm for solving that type of problem, that provably solves that type of problem. So that's an amazing algorithm. The only slowdown, there is a little bit of a slowdown, which is just a constant slowdown. So it's as fast as the fastest method, except for an additive constant that disappears as the problems get larger and larger. As, for example, you are trying to solve a traveling salesman problem, and the number of cities gets larger and larger. This additive constant becomes negligible. And so we can say that today most problems are solved because most large problems are solved, because almost all problems are large problems, and there are just a few small problems. And the only reason why this is not the computer science end is that within this universe, there are lots of small problems that are so small that the additive constant, which hides the complexity, the constant effort requested by a proof searching technique, it hides it. In this universe, these constants still are relevant because the problems are so small. Now, can you do anything about these constants? Yes, you can use an old trick of Kurt Gödel, who in 1931 founded theoretical computer science. You can produce a self-referential Gödel machine. I will tell you something about that in a second. Here we see a picture of Gödel, and he in 1931 used the integers as a universal programming language, and he used it to describe or to create formulas that talk about themselves, that are self-referential, and they say things such as, I am not provable by a computational theorem proving procedure. And in this way, he showed that math is either fundamentally flawed or contains statements that are true but not provable. And he was an Austrian. He did this work in Vienna, but later he came to the United States, just like another great Austrian thinker who then became governor of California. And we can use the self-reference trick of Gödel to build another type of optimal universal problem solver, which is totally self-referential in the sense that it can inspect any of its code and can rewrite any of its code, provided that it first can show through a proof that the rewrite is good according to some user-defined utility function, which can be anything. Any problem can be written, if it is well-defined, as a utility function. And so we have a self-referential machine. This is a rather novel application of Gödel's self-reference trick, which can be used to build a universal problem solver, which again is theoretically optimal in a certain sense. And if you really want to understand the details of that, you can download pages and papers on this. But here I just want to point out that we are currently entering, through results like that, into a phase where AI, artificial intelligence, is not any longer just a collection of heuristics, but it is becoming a real formal science like probability theory and established sciences like that. And that's good because heuristics come and go, but theorems are for eternity. And this reminds me that in just a few months, we will have the next Artificial General Intelligence Conference in Lugano. The first two were here in the United States. And the deadline for submitting papers is 15th October, I believe. Now, the main message of my talk is that any understanding of intelligence would be incomplete without an understanding of things such as art and science and music and humor. And I will show that there's a very simple algorithmic principle that can explain these things. It's so simple that it fits on a single slide, in principle. So that is now the most important slide of my entire talk. It contains my take-home message for you. If you understand that slide, you understood everything. There are still people coming in from lunch. Maybe I should wait a little bit until everybody's seated. But what should an unsupervised intelligent agent, be it a human baby or an artificial agent, what should it do? How should it deal with the data that is streaming in through the input sensors in response to the actions that it's executing? But first of all, and this is a very trivial thing to do in principle at least, is you should store all the data that is coming in. You shouldn't throw away any of the data if you can. And it makes sense, because within a couple of years we will be able to store 100 years of lifetime at the resolution of a high-definition TV video. And maybe human brains also can store 100 years of human lifetime at the rate of maybe, I once made a rough calculation of about, well, comparably to a low-resolution MPEG video. So in principle, that is not a problem, but with that by itself, you cannot do anything. You have to find regularities in this history of inputs and actions that you store, and in other words, you have to compress it. You have to compress the history. Whenever there's a regularity, a symmetry, or whatever, then you can write a program that needs less bits than the raw data and still encodes the entire data. So that's what compression is about. Now let's define the simplicity or the subjective compressibility or the subjective beauty of some data point X given some subjective observer O at a given point in his life t. And that is just the number of bits you need to encode the incoming data, the x, at this point in time with the given limited compression algorithm that you have. For example, most of you know a lot about human faces. And And that's because you saw so many of these faces, and now you are carrying around with you some sort of prototype face, which allows you to encode new faces in the visual field by just encoding the deviations from the prototype. So whenever a new face comes along and it looks very much like the prototype face, then you just need a few extra bits to store that new face. And your lazy brain likes that because it doesn't want to waste a lot of storage space. So the more the face looks like the prototype face, you could assume the fewer bits you need to encode it, and the prettier, in a certain sense, you find it. This is just a word. We just count the bits that we need to store the new incoming data. For example, a face that is very regular doesn't need a lot of bits to be encoded. All right. Now, the important thing is not the compression by itself, but the first derivative of the compressibility, because what's really going on is that as new data is coming in, your compression algorithm improves all the time. It improves all the time and becomes a better predictor of the data. Whatever you can predict, you can compress, because you don't have to store extra what you already can predict. So prediction and compression are almost the same thing. And to the extent that your learning algorithms is improving the predictor, such that it becomes a better predictor on the observed data so far, you are saving bits. You can count this progress in bits that you are saving. And that's the only interesting thing which signifies that there's a novel pattern in the input stream where you still have some learning progress. So what you're interested in is, or what is the interestingness of some data X? Well, it's not the number of bits that you need to encode the data, but it's the first derivative, the change of the number of bits as your subjective learning algorithm, based on your subjective previous knowledge is improving the compressibility. So you have to count the number of bits that you're saving. And then, once you have that in place, and it's all, you can formally nail it down and implement it on computers and robots. Once you have that, then you just need an additional algorithm, an additional learning algorithm, a reward optimizing algorithm, which takes all these internal joy moments. And whenever you save a few bits, it means you have a novel pattern, and you count how novel it is by counting how many bits did you save. And that's an internal reward signal, an intrinsic motivation, an internal joy signal. And that's what you want to maximize for the future. You want your controller that is directing your arms and your actuators to move such that you get additional data from the environment where you can still get additional types of compression progress of this type, where your particular compression algorithm still can make this type of progress. And there are many reward maximizing algorithms and reinforcement learning algorithms that in principle can do this. And this is the basic principle, and I'm going to explain in the rest of my talk only how this explains art and science and whatever. So again, in discrete time, the formulation without derivatives, if you don't like that. The simplicity or compressibility, or beauty, if you want, of the data is the number of bits you need to encode it, given what you already know about the data. But then, the interestingness of the data is the change in the number of bits. So you get the data, you learn a little bit on it, which means you can now compress it a little bit better. So the raw data is like that. The compressed data is like that. Then you improve the compressor a little bit, it learns something, it becomes a better neural network that predicts the data, and now it takes so many bits. And this is what you save. And that's your internal reward signal, because you have a novel pattern which you didn't know yet. And that's why you find it interesting, and you can just subtract the number of bits you needed before from the number of bits that you need afterwards, and there you go. So that's the reward signal. Let me give you an example, a very simple example of a robot sitting in a dark room. The input doesn't change. It sits there, and no matter what it does, it's always black, black, black. So it's extremely compressible input. But because it already can predict that very easily, because you just can predict by saying the next frame is exactly like the previous one, you can totally compress the input, and it's totally boring because there is no compression progress, because you don't see a pattern that you didn't already know. Now let me give you another extreme example, which is just the opposite. Suppose you're sitting in front of a screen with white noise, and there are all these black and white pixels coming with equal probability at you, conveying maximum traditional Shannon information or Boltzmann information, and still this stream of inputs is totally boring again because, yes, it's very uncompressible, you cannot find a short pattern, and you cannot improve your current description of the signal, which again means that there is no compression progress. So this is also boring. The only thing that is interesting is stuff like certain types of music, which you didn't know yet, but which is maybe a little bit similar to what you already knew about music, and whether there's a new little harmony in there which you haven't heard just in this way, and there you have a little pattern where you save a couple of bits, and then that's what motivates you to listen to the same song again once more. All right. So here we have again boring white noise and no internal reward for things like that. So a discovery in physics, for example, is just a very large compression improvement. For example, suppose you have 1 million videos of falling apples, and they all fall in the same way. It's always the same way they fall down. So you can, when you're good, you extract the rule. You can extract the rule behind this behavior, and it turns out it's a very simple program that describes gravity essentially, and it's always a very short program that you can use again and again for all these many different videos of falling apples to greatly compress these orange blobs that are falling down there. You cannot compress everything. There are random fluctuations and noise and whatever that you can compress, but there's a substantial aspect of the incoming data that you can compress. And there you can make a lot of compression progress, suddenly save a lot of bits. But the same is true also in the arts. Suppose there's a guy who figured out a way of drawing Obama with just 5 lines, such that everybody says, hey, that's Obama. So you have an artist who somehow extracted the essence of the face, such that you have the same impression as you're looking at this face that you get when you are looking at a high-resolution photograph with 1 million pixels. So somehow there was a compression progress in the artist as he was trying many times to come up with a convincing caricature, and there is a similar thing happening in the observer when he sees that for the first time. So the scientists and the artists have something in common. They always try to make new data which is compressible in a new, previously unknown way. A new pattern, a novel pattern means, yes, it's compressible, but in a way that I didn't know yet, such that my compressor can make this learning progress and can save a couple of bits. You know, before I came here, I thought this is going to be just another Singularity Summit, and probably there won't be much of an audience, but you are actually a large audience by my standards. The other day, I gave a talk, and there was just a single person in the audience. A young lady. I said, young lady, it's very embarrassing. But apparently today I'm going to give this talk just for you. And she said, okay. But please hurry, I gotta clean up here. We had a whole bunch of different implementations of the principle that I just explained. We didn't start that yesterday. In 1990, the first systems of this type were implemented using very simple prediction machines, artificial neural networks. How many people know what is an artificial neural network? All right, okay. And so you can use them to become better predictors and better compressors of the data history. And then we had additional systems like that, but I don't even have the time to go through that. I would like to mention, though, that recently 2 guys in California, they took the 1995 model and found that it explains eye movements of humans better than previous models. So why are you looking here and not there? Well, for some reason it's more interesting there than here. But what does it mean, more interesting? Well, because this action of looking there leads to a new input which leads to some input pattern that has something interesting. Why is it interesting? Well, because there is something which you don't know exactly yet and where you can still make a little bit of learning progress. You can save a few bits. And that's what's driving all the interesting, all the curiosity, but also the creativity of any intelligent system. Creativity and curiosity, just the same aspects of the same principle. trying to make new data, more data, which is compressible in previously unknown ways. And we are currently implementing in a more complex system these principles on a humanoid like this, which is called the iCub, and there's a big European project where where the goal is to implement these principles such that you have all these things again in place. You need a predictor or compressor of the data that improves over time, and all the new data that is coming in, it's getting more and more data, but you constantly try to compress it, and then you constantly try to find new patterns, better ways of compressing, and then you get the motivation for the controller that is selecting the actions, the eye movements, the dances, or whatever the robot executes, which lead to new patterns that aren't already in his repertoire. So directed exploration of the world through science, or just like a baby that is exploring what can it do with its fingers, etc. I think it's all driven by this very simple, basic principle here. Let me give you a little example, an application of this. I tried 1,000 times to come up with a very simple geometric description of human faces, and usually everything you try, it really looks bad and stupid and awful, and suddenly something comes along which doesn't look so bad, you know, and then you see, oh, there's a simple geometric scheme. Now this one here is a binary scheme which is based on certain very simple coordinate systems, and you always take half of the original grid that you get there to define then all the basic features of this face, like for example the slant of the eyebrows, the thickness of the eyebrows, the slant of the facial sides, and all these things. And it takes a long time to come up with any geometric schemes that make sense at all. Most of them just look horrible. Now, of course, I'm not the first guy who's trying to do that. Leonardo da Vinci himself, he also tried to come up with proportion studies where you define the basic facial features through mathematical rules, but not to the same extent, not in the sense that you really describe all the slopes and all the details of these images, of these facial structures. Now, this face, of course, is interesting only as long as the regularity in it, the symmetries, etc., are not yet known, but then it becomes boring. Like every data that you see, over time it becomes boring, because once you understand what's going on there, and you see and incorporate the regularity and the short program that describes it, it gets boring and you want to see something else. Let me give you another example of very compactly encoding images. Let me start with a bunch of large circles, which look very much like what many kids draw with a circle when they're young. And then we add 4 times as many circles with half the size. And then we add 16 times as many circles with 1/4 the size, and so on. So you see it's getting more and more circles. And now the rule is I can create new drawings, but only by using arcs that are on these legal circles that I get there. And there are a few large circles and many small circles. Now I can encode drawings like this one here, for example, by just describing, by enumerating all the circles, for example, giving each of them a little number. The large ones get small numbers, the small ones get larger and larger numbers, and then you can very compactly encode drawings like this one here. Again, that's most of the things you try, they don't look like nothing, but if you try hard, then in the end you find something that is acceptable, and then you've got a low complexity artwork like this one. Now here I'm removing all the green circles, which I'm not using, and leave only the red circles, and which are the only ones that I need to specify the details of the drawing. And finally, I get a very simple drawing that can be encoded by very few bits of information, just a few lines of code, much more compressible than, for example, a JPEG encoding of the same image or a GIF encoding. And that would be then an example of low complexity art, which I defined in 1997 in a journal which is dedicated to such things. Leonardo is the journal. And let me give you another example. Again, the same scheme, which can be used to very compactly encode drawings that follow these basic rules. And here we see a self-similar femme fractale. So I'm removing all the circles that I'm not using, and then only the green circles are left, which are the only ones I need to specify the details of this drawing. And then finally, we have, again, an image, a low-complexity artwork, if you want, that can be encoded by very, very few bits of information. What is next in artificial creativity and artificial curiosity? Well, our first implementations, they use these feed-forward networks, which are just devices that learn to map an input to an output, and over time become better mappings between inputs and outputs. But now we are much more focused on these recurrent neural networks. Recurrent neural networks, how many people in this room know what that might be? Recurrent. So that's a mathematical model which is very much well, it seems a lot like what your brain is doing. It has feedback connections that allow it to implement arbitrary programs, mapping arbitrary input sequences to arbitrary output sequences. So it's a general computer, and it turns out that there are ways of training the weight matrix of these recurrent networks, which implement the program such that the whole thing becomes a better description of the data that you want to model with it. And just to give you a few examples what you can do with these things, this is a picture of Alex Graves, my postdoc, who used to be a PhD student at SIA, but now a postdoc in München. And currently the best connected handwriting systems are using recurrent networks like this. So there are particularly useful variants of recurrent networks that we developed at SIA, and they are currently the state of the art in connected handwriting recognition, which is much harder than isolated digit recognition. And what else can you do with that? Or you can predict time series like this. So here you have a time series, and it looks a little bit like a stock market chart maybe, and you give that to your investment advisor, and he's supposed to predict the future of that, but mine is completely unable to do that. But then our networks can pick up the regularity. There's a regularity in this curve here, and very exactly predict the future without seeing it. So that would be another application. Or you have robots that have tiny little actuators, and they are working on, well, they are designed to work in surgery settings, and you have a surgeon that shows them how to do and how to tie a knot in very confined cavities, which is hard. But this is then the first robot that learned to tie knots like that using recurrent neural networks, like the ones that we developed. But so once you've got these compression machines, these recurrent networks, which are just supervised compressors of the data history, and they become better and better at predicting the data, and therefore also can become better and better at compressing it, then you have to look at what happens to these reward signals that you get as you are getting a better compression. And then these reward signals, they go to the reward optimizers, to the reinforcement learning algorithm. And what is a good choice? We often use certain novel techniques for co-evolution. Let me see whether I can get the cursor going there. Oh, there we are. So up here, we see we see a little robot which has learned to balance a pole. Maybe you see that. It has 3 wheels. It's controlled by, again, a recurrent neural network. But now there's no teacher that tells the robot what to do. In the beginning, the pole always fell down. But then after some time, it maximized trial length and became better and better. But then it was starting to run against the wall all the time. And finally, it learned to use its sensors without a teacher to go away from the wall whenever it's getting too close. And down here, let me see. Down here we see the same robot, but now with 2 poles on top of each other. So now here there's a joint in between, and this robot, after 4,000 iterations, trials, has learned to balance another pole on top of the first one. Here you see that. But now it's not perfect yet. I showed you something which isn't perfect yet, just to show you that there's really 2 poles on top of each other. 1,000 iterations more, and it knows how to do that. Or here there is an object which is moving through water, and then it's generating turbulence. Now what you want to do is you place little tiny actuators on top of this object such that they create little tiny anti-turbulences which kill the vortices, such that you can reduce the drag of the object. So the goal is to reduce the drag. And let me show what happens if I run that here. Okay, so here you see a supercomputer simulation of the vortices in the back, and down there here you see what happens after learning. So first we see what happens before the learned behavior is switched on, and suddenly you will see that these vortices get really small because the system has learned to generate anti-turbulence, again through one of these reward optimizing algorithms. And the drag goes down from to 40% of the original value, which was an excellent result a couple of years ago. So that's what you can do. How many more minutes do I have? I still have 10 more minutes. Okay, so I have only 2 more slides to go, maybe 3. I want to put all of this now into this historic context, which is the main topic of this conference. Here we see the beginning of the computer age. 1623, Wilhelm Schickard, he built the first computer. You couldn't program it, but you could do the basic arithmetic operations already, and it didn't have transistors, but it had gears, but nevertheless you could compute with this thing automatically. And then for a long time nothing happened, but then Babbage came along in England. 2 centuries later, in the 1830s, he came up with this idea of having a program-controlled computer, and this is considered as another major milestone in the history of computing. His machines did not work. Even 20th century replicas of these program-controlled computers didn't work. But at least the idea was there. And then we had to wait only 100 more years, 1 century later, and modern computer science started. Because this guy here, Konrad Zuse, he built really in 1941, he completed the first computer that really was working, a program-controlled working computer. And in the decade before that, the foundations of theoretical computer science were created through Gödel, whom we already know, and Turing then took the results of Gödel and rephrased them in this in the context of the famous Turing machines, which are now still widely used in theoretical computer science. And you know, just a few years earlier, this guy, Julius Lilienfeld, can we see that? Julius Lilienfeld, he, in the 1920s, and it happened within, 10 years or something. Another Austrian, Hungarian, by the way, who also later then emigrated to the United States. And then lots of things happened, but the main breakthrough after that, or the thing that, again, changed everybody's life, or lots of lives at least, was the World Wide Web, exactly half a century later. Now you see the pattern. So Tim Berners-Lee in Switzerland, he came up with the World Wide Web, and within a few years it affected the lives of billions. Now you see the pattern between the major milestones: 2 centuries difference, 1 century to the next major, now 1/2 century, and you can generate a logarithmic plot, and you can easily fit a straight line. No, it's going to converge, obviously, because the next thing is going to happen not 1/2 century, but 1/4 of a century in 2015, where many people claim that computers will be as fast as human brains for the first time. And then we will have an infinitude of additional milestones, and they are going to converge in 2040, which is the omega point, which I like better than the singularity. I like omega much better than singularity, because that's what Teilhard de Chardin called in 1900 when he said humanity will reach its next level. Also, I like it because omega, it sounds so much like, oh my God. There's only one problem with lists like that, which is that actually omega should not have, will not happen in 2040. It should have happened already in 1540. In 1540. I can prove it to you. I can prove it to you. At the turn of the millennium, Life magazine made a list of the most important inventions, or most important events of the millennium. And their number 1 was the invention of the printing press, 1444 by Gutenberg. And then the second most important event in the history of the past 1,000 years, according to Time Life magazine, was the discovery of America through Columbus. Of course, many people know that other people before Columbus, like Leif Erikson and probably others, also discovered America, but Columbus did not become famous because he was the first to discover America, but because he was the last to discover America. And now let's look at the next, at number 3 in Time Life list of most important event, and that was the Reformation, according to Time Life magazine, probably because it was the only major religious movement of the past 1,000 years. And you see, there's a pattern, 96 years, and then between these two events there are exactly 48 years, and then half of that, 24 years, you know, it's about to converge in 1540, you know. And so, of course, there never has been a shortage of prophets claiming that the end is near. And maybe all of this is just a byproduct of the way we are allocating internal memory space to events in our past, because look at yourself. Most of your mind is occupied with things that happened recently, yesterday, a week ago, not so much a year ago, not so much 10 or 20 years ago, etc. And the same is also true, of course, for history books of societies. Entire societies write a lot of history books, but most of the history books are about the most recent events. And not so many, still a lot, but not so many are about, say, the Second World War, and 200 years ago, things. And the further you go back in time, the fewer history books you will have. And of course, this is just a natural thing. You allocate less and less storage space to events that are more and more, or deeper and deeper in the past. So, from that point of view, at whichever point in time you live, it may look to you that the most important things are accelerating exponentially, you know? It doesn't really matter when you live. So, yes, I really have to go. Okay. All right. Think about that. Thank you very much for your attention. Are you saying there's no time for questions?
No, you went right.
Oh, but Ray Kurzweil said he is going to compensate by speaking faster. All right. So.